Awesome. So we left off on looking and reminding ourselves that this top row is our original rectangle ABCD. And then we have our larger rectangle that we doubled the side lengths and we saw our perimeter also doubled, 20 to 40, and our area quadrupled. We took 24, multiplied it by 4 to get 96, and we're focusing on our smaller rectangle, which was a 2 by 3, which we said, well, that area is 10 because you add up both the heights and both the widths. And then our area is 6 because that's when you multiply 2 times 3. And we saw that our change in the lengths, we were told that's half the original. And we saw that our perimeter was also half. How do we go from 20 to 10? We take half of 20 to get 10. And then we say, okay, well, what about the area change? Do we take half of the original area? No, if we took half the original area, we'd have 12 here, but we have 6. So what do we do to 24 to get to 6? We half it and half it again. That means we take 1/4. 1/4 of the original. Remember, we're always comparing back to the original rectangle we were given. So when you have to fill out a table like this on your own later, this first column is always original, original, original. Awesome. So it's very interesting how we go from doubled to quadrupled. We go to 1/2 to 1/4. There's an interesting relationship here. And this relationship is going to help you out on your mu and for the rest of this activity. So let's look at activity 2. The directions are on the bottom of this page, but the activity itself is on the next page. So let's start reading. Please have your trackers ready as I'm reading aloud. Activity 2. Below, aka on the next page, is an image of rectangle MNOP, which is 3 units by 6 units. On the first grid provided, draw a rectangle with side lengths that's 3 times as long as the image. Label a new vertices Q, R, S, T. And on the other grid, we're going to draw a rectangle with side lengths 1/3 as long as the image. And label these new vertices U, V, W, X. So remember, this is MNOP, and we're going to label our second rectangle, which is 3 times as large, as a rectangle QRST. And we're going to have our other rectangle that's 1/3 as large. We're labeling that rectangle as UVWX. Awesome. So why don't you take a little time with your groups, and I'd like you to finish this page. Please pause the video for 5 minutes while you create these 2 rectangles and fill in the chart below. Please pause the video for 5 minutes to complete this entire page with your groups. Awesome. Let's see how we did. So taking a look at our grids, hopefully you used a straight edge of some sort and your rectangles look a little nicer than mine. We have QRST is a 9 by 18 and UVWX is a 1 by 3. So let's take a look at our chart. Again, QRST is a 9 by 18, which gives you a 54 unit perimeter. 9 plus 9 plus 18 plus 18, or 2 times 9 plus 2 times 18. Our area, 9 times 18 is 162 square units. And our lengths we tripled. Because we tripled our lengths, we noticed that our original perimeter to our new perimeter also tripled. 18 times 3 is 54. And if we take a look at our area, how do we go from 18 to 162? Well, I grabbed a calculator and thought of 162 divided by 18 to find out that 18 times 9 is 162. So if you multiply your original by 9, when we multiply by 9, we get our new area. Tripling is multiplying by 3. And here we're multiplying by 9. Interesting. Let's look at our other rectangle. We end up UVWX with a 1 by 2. That perimeter is 6 units and the area is 2 units squared. Notice we changed the side lengths by a third of the original, and our perimeter is also now a third of the original. To go from 18 to 6, we'd multiply by 1/3, or divide by 3. 18 times 1/3 is 6. Well, how do we go from the area? What do we multiply 18 by to get to 2? What do we multiply 18 by to get to 2? Well, we would divide by 9, so that's 1/9 of the original. How do we go from 1/3 to 1/9? Notice these are always the same. However you're changing the side length, the perimeter stays the same because they're the same dimensions. They're both one dimension. Here, though, we're squaring the side change. If we're tripling, squaring means multiplying that number by itself. So 3 times 3 is 9. And 1/3 times 1/3 is 1/9. And I'll show you that. 1/3 times 1/3. Remember, we multiply across with fractions and get 1/9. And if we go back to our first page, we can see that same pattern. If we take 2, what we're changing our lengths by in our perimeter, what's 2 times 2? 4. And here we change the side lengths by 1/2. What's 1/2 times 1/2? 1/4. So we can find the factor that the area changes by without necessarily always calculating the area. That's very interesting. Let's continue our activity on page 37 with activity 3. Now we're going to be looking at another shape, and let's see if these relationships continue if we're dealing with a triangle. So below is an image of a triangle, ABC. On the first grid provided, draw a triangle with side lengths that are twice as long, and we're going to label these vertices as this is going to be triangle DEF, most def. And on the other grid, we're going to have one that's half as long. And this new tinier triangle is going to be triangle GHI. So let's remind ourselves a few things about when we were doubling. We just talked about moving, how far we move from one vertice to the next. So just like before, when we want to go from A to C, we went up 1, 2, 3, 4, and over 2. Which means now to go from A, before we're going A to C, so now we're going to go D to F. To go from D to F, I need to first graph D. Instead of just going up 4, I need to go up double 4, 2 groups of 4, 8. 1, 2, 3, 4. 1, 2, 3, 4. And I'm not going to place a point there, because then from there I need to go right 2 groups of 2, twice 2 or 4. 1, 2, 1, 2, to get my coordinate F. So here we have line DF, which is twice the distance of line AC. Now let's continue AB. Let's find DE. A to B is 8 units to the right. So from D to E, we're going to go 16 units to the right. One. Just fit. Okay, and that is vertex E. And then what we can do is we can just connect these two and double check that to go from B to C, we go up 4, and here's 2, and this whole distance 8, so this must be 6. So I should have to go up 8, double 4, and to the left 12, double 6 to get to F. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, double 4, and we have to go double 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Excellent. I would say that this triangle DEF is double the distances of side lengths triangle ABC. Wonderful. So let's take a look at if we are halving. Let's take a look if we are halving the triangle. So again, if we're going to move from A to C, we go up 4 and right 2. That's to go from A to C. So if we're going from G to I, let's plot G, and we're going to go half the distance up vertically. Half of 4 is 2. And we're going to go right half the distance horizontally. Half of 2 is 1. And that's how we're going to end up at point I. And we're going to connect GI. Now we want to half the distance of 8. 8 was AB, so when we're looking for GH, half of 8 is 4. 1, 2, 3, 4. So here is H, and here is our triangle where the lengths are half the distance of our original. So when we doubled the length of each side, we doubled each distance with corresponding direction and points. And to half the lengths, instead of doubling each distance with corresponding direction and points, we halved the distances with corresponding direction and points. Directions and points. Excellent. Do you think the angles of our new triangle are the same or different than the original triangle? Explain. Well, let's take a look. Do all these angles look pretty much the same? Did they double the angles when I doubled the side lengths? Or half the angles when I half the side lengths? Not at all. All the angles, we call this preserving. Preserving means it didn't change. So all the angles stayed the same. Or we can say preserved. Very mathematically elite. Only the side lengths extended or shortened, but the angles stayed the same. The only thing we changed were the side lengths. Awesome, let's continue working. What do we think is going to happen to the perimeter? What do you think is going to happen to the area? So I'd like you to think about this with your groups for 2 minutes. So pause the video for 2 minutes and discuss, what do you think is going to happen to the perimeter? And what do you think is going to happen to the area? The relationships are the same relationships as our first two activities. When the side lengths are doubled, your perimeter is also doubled. If your side lengths are halved, the perimeter is also halved. So when the side lengths of a polygon, so a triangle, a square, an octagon, any polygon, are changed by a factor, like this factor is 2, the perimeter is changed by that same factor proportional. So we know that side lengths and perimeter are proportional. The lengths changed by the same factor. The side length is doubled, the perimeter is doubled. The side length is halved, the perimeter is also halved. If you need to pause the video to copy this down, please do so and continue. What did you notice happened to the area? When the side lengths were doubled, the area was quadrupled. Meaning, before it was twice as much, now the area is 4 times as much. When the side lengths were halved, the area is quartered. 1/2 squared, 1/2 times 1/2 is 1/4. So we see that when the side lengths of a polygon are scaled by a factor a, the area is scaled by a factor of a squared, a to the 2nd power. So I'll give you a moment to make sure you write this down.